Hello and welcome to Shridevi classes where we inculcate interest and confidence in subjects by removing all doubts and confusions. Today, to remove your confusion in physics, we'll understand the concept of common potential when capacitors are connected in parallel. If you won't devote next 10 minutes with us and if you found this question pattern in your exam, then won't say I left behind. फिर ना कहना रह गया. So let's understand the concept of common potential. First, understand the problem related to finding out common potential. When we are given two or more capacitors having different potentials on them after charging, and if such capacitors are connected parallel to each other, then charge on plate will have to redistribute so as to achieve the identical common potential in parallel connection. And in such conditions, the capacitor which have earlier higher voltage will release its charge to another capacitor having lower voltage, and ultimately both will attain identical potential. So this is a problem of potential equalization by charge redistribution. When two capacitors of two different potentials are connected in parallel, the capacitor having higher potential will release its charge and its charge will reduce from say Q1 to Q1 dash, and at the same time the capacitor having lower voltage will receive charge and its charge will increase from Q2 to Q2 dash, and ultimately both will have common potential. But during this charge redistribution, the total amount of charge on capacitor plate, which is earlier Q1 plus Q2, will remain the same as Q1 dash plus Q2 dash. So there exists the concept of charge conservation in this phenomena, and ultimately when both capacitor got identical equalized potential, the charge circulation will stop. And this particular condition, when two parallel connected capacitor attain common potential, is the position of minimum potential energy of this charged capacitor system. This is also the most stable position of this parallel connected charged capacitor system. Let two capacitors of capacitance C1 and C2 are charged to potential respectively V1 and V2, and V1 is greater than V2. Now in this charge condition, the charge on capacitor 1 is Q1 and it is given as Q is equal to CV as C1 V1. Similarly, charge on second capacitor is C2 V2, and when these two capacitors are connected in parallel, the charge of two capacitor plates will redistribute such that charge conservation will holds true, and after redistribution, when the parallel connected capacitor attain identical common potential, the charge on one capacitor Q1 dash and charge on second capacitor Q2 dash is given as C1 plus C2 multiplied by V, where V is the common potential of this parallel system of two capacitors after charge redistribution. So initially when capacitance C1 got a potential V1, its charge Q1 is C1 V1, and capacitance C2 with potential V2 have a charge Q2 equal to C2 V2, and initially two positive plates got total initial charge C1 V1 plus C2 V2, and after redistribution of charge when common potential V is attained by two capacitors, the charge on first capacitor C1 V and charge on second capacitor C2 V when summed up give us final charge on two capacitors. And as per conservation of charge, initial sum of two charges and final sum of two charges should remains the same. Initially two capacitors are isolated and have different voltages, and finally parallel connected capacitor got common potential. So initial charge C1 V1 plus C2 V2 is equal to final charge C1 plus C2 V, where V is common potential, and we can find out common potential as total amount of charge on two capacitor divided by sum of capacitance of parallel connected capacitor. And if V1 is greater than V2, then this common potential will be less than V1, as this capacitor will release some charge to other capacitor and the voltage of V2 will increase to V. So one capacitor lose its charge and potential having higher voltage, and another of lower voltage attain additional charge and increase its potential. And here we can say common potential is nothing but the ratio of total charge to total capacity capacitance in this configuration, and it clearly shows that charge is lost by capacitance having higher potential and charge is gained by another capacitor having lower voltage. As after charge redistribution, this position of common potential is more stable position, so it have less amount of stored energy than isolated two capacitor. So there exists a loss of energy in this charge redistribution, and this loss can be obtained as initial stored energy on two capacitor subtracted by final stored energy in this capacitor configuration of common potential. Now the stored energy is given as half CV square for first capacitor and second capacitor having different voltage V1 and V2. And finally, the equivalent capacitance of parallel connected capacitor is C1 plus C2 and common potential is V. So the stored energy finally is half CV square. When the subtraction of initial and final stored energy is obtained, then in place of this common potential, we can write total amount of charge on capacitor divided by equivalent capacitance of parallel connected capacitor. Half is brought out as common here, and C1 plus C2 become LCM for this expression, and when this is multiplied by C1, it becomes C1 square V1 square, and when this is multiplied by C2, this becomes C2 square V2 square, and this multiplied by C2 and this multiplied by C1 gives these two expression, and this square when expanded become A square B square plus 2AB. Now in this expression, these terms C1 square V1 square and C2 square V2 square get cancelled out, and when we brought C1 C2 in numerator common and in denominator we have C1 plus C2, then this remaining expression becomes V1 square plus V2 square minus 2 V1 V2, and this is nothing but V1 minus V2 whole square. And we can say loss of energy in charge redistribution is half C, that is equivalent capacitance of series connected capacitances, multiplied by V square, where V is the difference of two potential V1 and V2. Higher the potential difference between two capacitors, higher would be the loss of energy in charge redistribution to attain common equalized potential. Let's understand the concept by numerical example. A capacitor of capacitance 2 microfarad is charged to 250 volt and it is connected to another capacitor of capacitance 3 microfarad which is uncharged having zero potential. We have to find out common potential between two capacitor, one having 250 volt and second having zero potential, and in the process we have to calculate the total amount of energy loss. So initially 2 microfarad capacitor with 250 volt got Q is equal to CV 500 microcoulomb charge, second is uncharged, so total initial charge is 500 microcoulomb, and finally if common potential is V and two capacitor got equivalent capacitance 5 micro, then it is 5V microcoulomb charge, and from this charge conservation relation 500 microcoulomb become 5V microcoulomb and common potential comes as 500 micro divided by 5 micro as 100 volt. So two capacitor having different voltage 250 and 0 when connect in parallel will have common potential of 100 volt, and in the process loss of stored energy is half equivalent series capacitance multiplied by difference of voltage square. So it is C1 C2 divided by C1 plus C2 microcoulomb, and one got 250 volt and second got 0. This 2 get cancelled out by this 2 and this 5 when simplified. Then finally we got loss of energy as 30 by 80 joule, and in this charge redistribution the loss of energy takes place in three following way. One is I square R loss in connecting wire and contacts of capacitor when charge redistribution associate flow of current in these connecting wire and contacts, and resistance of those wire and contacts will have I square R loss. One important loss is electric spark, which will take place when two capacitor of different voltage are initially connected together, and in the sparking process there is also emission of electromagnetic radiation, and that also have some associated energy loss. Let's understand another example. A parallel plate air capacitor is charged to potential V volt, and there is another geometrically identical parallel plate capacitor but with a dielectric of mica, and this second mica capacitor is uncharged, and now the two capacitors are connected together, and after charge redistribution common potential comes as V dash. We have to find out dielectric constant K of mica. Let the capacitance of air capacitor is C, and similar mica capacitor of dielectric constant K would have capacitance Kc, and as per conservation of charge, initial charge only on air capacitor is Cv as mica capacitor is uncharged, and finally with common potential V1 the two capacitor in parallel got equivalent capacitance C plus Kc, or 1 plus K multiplied by Cv dash is final charge on two capacitor as per charge conservation. Initial charge and final charge can be equated to each other. So 1 plus K when C get cancel out will become a ratio of initial voltage on air capacitor divided by final common potential, and K, the dielectric constant of mica, is V divided by V dash minus 1, and when LCM is taken, this would become our value of dielectric constant of mica. Let's end this important and conceptual video with one more numerical. Two 10 microfarad and a 20 microfarad capacitors are connected in series across a 200 volt supply, and after charging in series connection both have same charge but different voltages. Capacitor of lower capacitance will have higher voltage, and now these two charge capacitor are connected together in parallel with positive plate of one is connected to positive plate of another, and we have to find out common potential in this case. So for common potential we have to find out the total charge on capacitor, and we have to divide that by total equivalent capacitance of parallel connection configuration. So in series connection, equivalent capacitance of two capacitor C1 and C2 is product by sum, and it comes as 20 by 3 microfarad, and on this equivalent capacitance when total voltage is applied, the charge on capacitor comes as Q is equal to Cv as 4000 by 3 microcoulomb, and both capacitor having 4000 by 3 microcoulomb charge when connect together will have double amount of charge, and total charge divided by equivalent capacitance comes as common potential as 800 by 9 volt. We hope this and other video of our Confused in Physics series helps you in your examination. You can also search top 20 learning video in our playlist to get better marks in your board examination. Happy learning. Have a nice time. Thank you very much.